Welcome to Aquatic Biology. Today, we are going to explore a fascinating and invisible phenomenon that happens in deep lakes all over the world, known as thermal stratification. We will discover how this simple heat from the sun creates distinct layers of water that refuse to mix, and why this physical separation is a matter of life and death for the entire aquatic ecosystem. To understand how this works, imagine drawing a deep bath. If you turn off the hot water halfway through and fill the rest with cold water without stirring, you will feel a distinct hot layer on top and a freezing cold layer at the bottom. This is exactly what happens in deep lakes during the summer. The sun acts like a giant heater, warming the surface water. Because warm water is lighter than cold water, it floats on top. This creates invisible but very real layers, much like a liquid layer cake, where the layers refuse to mix because they have different weights. Now that we have visualized these layers, let us formally identify them. Thermal stratification separates a lake into three primary zones. The top layer is the epilimnion. This is the warm, well-mixed upper layer that constantly interacts with sunlight and wind. Right below the epilimnion lies the metalimnion. This is a transitional zone characterized by a very rapid drop in temperature. The steepest part of this temperature drop is known as the thermocline. You can think of the thermocline as a sharp boundary line separating the warm surface from the depths below. Moving past that sharp boundary of the thermocline, we reach the final layer. This bottom layer is called the hypolimnion. It is cold, dense, and rests completely undisturbed in the darkness at the bottom of the lake. The reason this heavy water stays at the bottom is due to a unique physical property of water. Water is actually at its heaviest, or most dense, at exactly 4 degrees Celsius. As it warms up above this temperature, it becomes lighter. Therefore, the lighter, warmer water sits securely on top of the heavier, colder water, easily resisting the mixing forces of the wind. Let us look at this diagram to bring all these concepts together visually. On the left, you can see the cross-section of the lake divided into our 3 zones. The warm red epilimnion is at the top, where circular arrows show the water mixing. Below it is the gradient of the metalimnion, and at the bottom is the deep blue hypolimnion. Now, look at the graph on the right. The horizontal axis represents temperature, and the vertical axis represents depth. Notice how the temperature curve stays high and flat in the epilimnion, then sharply drops exactly where the thermocline is, before leveling out in the cold hypolimnion. This visualizes the physical barrier perfectly. Seeing that sharp temperature drop in the diagram helps us understand its massive ecological impact. Understanding thermal stratification is absolutely critical because it dictates the life and death of aquatic organisms. During the summer, the thermocline acts as an invisible physical barrier. It prevents the oxygen-rich surface water from mixing with the nutrient-rich bottom water. If a lake stays stratified for too long, the bottom layer, the hypolimnion, can completely run out of oxygen. This creates a dead zone where fish and other animals simply cannot survive, trapping them in the upper layers. Fortunately, this dangerous isolation does not last forever. As the seasons change and autumn approaches, the air cools down, causing the surface water to lose heat rapidly. When the surface water cools, it becomes heavier and sinks. This allows the layers to finally mix in a vital event called turnover. Turnover is a lifeline for the lake. It redistributes life-saving oxygen from the surface down to the bottom and brings essential nutrients from the bottom up to the top. Without this natural cycle of stratification and turnover, our freshwater ecosystems would collapse. Before we look at the exact mathematical formula, we need to understand the concept of how scientists measure the strength of these water layers. The stability of a lake's stratification depends entirely on how drastically the density changes as you move deeper into the water. If the density changes a lot over a very short distance, the layers are locked tightly in place, like a heavy weight sitting on a lighter one. We represent this physical barrier using a concept called a density gradient. A strong gradient means a stable lake, while a weak gradient means the lake is vulnerable to mixing. Now that we understand the physical and ecological importance of these layers, let us look at how scientists actually measure their stability. The stability depends on how drastically the water's density changes as you move deeper. We represent this using the density gradient formula. G equals rho 2 minus rho 1, all divided by Z2 minus Z1. In this equation, G is the density gradient. The symbol rho represents the density of the water, so we subtract the upper density from the lower density. The symbol Z represents depth, so we divide by the physical distance between the two layers. When the density difference increases, G becomes a larger number. A higher value of G means the stratification is incredibly stable and difficult to mix. Let us apply this formula to a real-world scenario to see how stable a summer lake is. During midsummer, a limnologist measures the water at a depth of 2 meters in the epilimnion, finding a density of 997 kilograms per cubic meter. Down in the hypolimnion, at 8 meters, the colder water has a density of 999.7 kilograms per cubic meter. We want to find the density gradient. First, we subtract the top density from the bottom density, giving us a difference of 2.7. Next, we find the physical gap between our measurements, which is 6 meters. Finally, we divide the density difference by the depth difference. The result is 0.45 kilograms per meter to the 4th power. Because this number is significantly positive, it physically means the lake is highly stable and will not mix under normal wind conditions. Now, let us see what happens to our math when autumn approaches and the lake cools down. The surface water loses heat rapidly until its temperature matches the bottom. Now, the epilimnion at 2 meters has a new density of 999.7 kilograms per cubic meter, exactly the same as the hypolimnion at 8 meters. We apply the exact same formula. When we subtract the new surface density from the bottom density, the difference is exactly 0. We divide this 0 density difference by our 6-meter depth difference, resulting in a density gradient of exactly 0. Physically, this means there is no longer any weight difference between the top and bottom layers. Without this density barrier, even a gentle autumn breeze can easily stir the entire lake, triggering the vital fall turnover. We have covered a lot of ground today, so let us review the most important ideas. First, we learned that thermal stratification is a critical physical process where a lake divides into distinct temperature and density layers, with warm water floating above cold water. Second, we saw how the rapidly changing thermocline acts as a physical barrier, profoundly impacting the distribution of oxygen and nutrients, and sometimes creating dead zones. Finally, we calculated how seasonal cooling destroys this density gradient, allowing life-giving turnovers to occur. Understanding these concepts allows us to predict the health of a lake ecosystem and appreciate the delicate balance that keeps our freshwater environments thriving. You now have a solid understanding of thermal stratification,